Okay, we will talk more about that a little bit later. Now just review to remind you how to calculate the proton concentration in a salt solution. Okay, let's say this is your chemical formula. You dissolve that, and you want to calculate the pH for this guy. So notice this is going to be your starting material, okay? So dissolve that in water, then you're going to get these two products. So this is OH minus, and therefore you will be solving the X representing the OH minus. So whatever this concentration is, then you're going to get POH. Then pH will be the difference between that and 14, okay? Then a Kb here, how to get a Kb? So recall, this is not your Ka, right? This is your Kb. Then a Kb will come from the corresponding acid, the conjugate acid. So initially is a H3A, right? Initially is the formula is H3A, then go H2A minus to go HA minus 2 to go A minus 3. So we are talking about your starting chemical is way back here. So you know this is going to be Kb in the calculation. How to get it? You get it from here, from this Ka. So you're going to use Ka3 to get that Kb. Proceed with calculation. Okay, so remember that you will need to have the Ka3. Any question with this? Okay, good.
So that corresponds.
Yeah, go ahead, Jeffrey. That's fine. So the general calculation is this, right? So you're needing the Kb, Kw over Ka. Now where do you get the Ka from?
That'd be Kb3 though, right?
Will be Ka3. Ka3, well, whatever you can call this, Ka3 if you want. Some people call it the opposite, that's Kb1. Okay, so the nomenclature is not important as long as you know that Kb, where it should come from. Okay? Okay, now for this particular case, ordinarily, in most calculation, when you calculate the concentration for H2SO4, you may say that, okay, what's the problem? Just 2 times whatever that concentration is. Things like, 1 molar H2SO4, then what about the proton concentration? Then you may say that is 2 molar. Okay? But then you will see that is not quite true. Okay? Because of H2SO4, it is a strong acid, right? So one-way arrow, you're going to get HSO4 minus plus proton. The problem is, this guy is not 100% ionized. So you're going to have a two-way arrow to get the proton. So you get a Ka value right here. Okay? So here is a derivation for the proper formula that you need to employ. So we will go slowly here. Okay, so in this case, H2SO4, the first proton is going to be totally ionized, 100%, just like that. So what it amounts to, analytical concentration of the sulfuric acid. You start with that, then the tool will end up with that concentration. Okay, with the first proton. We are talking about the first proton. And this weak acid will carry initially this concentration. Now, the weak acid will ionize according to the Ka value. Okay, so it's written like this as what you are familiar with. Okay, at equilibrium now, then this concentration is equal to whatever that to start with minus x. That's what you are familiar with because the minus x translate into generating x for these. Okay, so this and that, let's call that the second proton. The first proton is that one. Okay, so the second proton is from here. This is the second proton. So that is equal to x. You don't know the amount until you calculate based on the Ka value, right? Okay, so second proton equal to x. A2 minus, they come from the same molecule. So when this is x, then A2 minus is going to be equal to x as well. So the second proton will be like that. So they are equal. Any problem with that? So we go slowly, okay? So one line at a time you can copy and understand rather than just go ahead and copy the whole deal without knowing where they come from. Okay, so here we're interested in the total amount of proton, right? So total amount of proton will come from the first proton. The first proton is right there, right? The 100% ionized first proton. Then the second one, okay, will come from the Ka ionization. So now we just write that down, it's understood. First and second proton together. Okay, then translating the first proton, we do know the concentration already, right? Because 100% ionized, so it's equal to whatever you prepare initially. Now, then we also understand that the second proton would be equal to the amount of A2 minus specifically ionized from the HA minus. So this represents the specific amount of the proton ionized, okay? So it's always useful to look at the coexist anion to that proton. Okay, so they are equal to x. Now we can write the proton total is equal to this is a value, this is an analytical concentration. So it's a real value, a number. So you can put it in, then plus the counter ion, which is uniquely representing the second proton. So that's why instead of writing second proton here, you write A2 minus, okay? Because it is unique to represent the quantity of second proton. So remember this trick. This is an important step, okay? So now you rewrite, then this put it to the left, then it's equal to the proton total. This is the x we are solving for. pH is based on this total. Then minus the numerical value, okay, in your experiment. Now, the basic. Well, for Ka, for the weak acid, Ka for the weak acid is equal to this expression. Okay, then now, with the above relationship, then you can rewrite, excuse me, rewrite so the top one stays the same. But the bottom one, you write it with a value minus the x, okay, because this one appears earlier up here, okay, HA minus is the same color, blue, as that. So you write it minus x. Okay, so this is minus x. Okay, then come down to here. The denominator will move to the left, multiply the Ka, and then this move to the bottom. So, okay, then let's see, where am I? Okay, the A2 minus here, the A2 minus here. So actually, you can just write the equivalence of A2 minus. Okay, so this A2 minus, the A2 minus is right here, equal to right there. So you put that in for A2 minus up here, and also A2 minus right here. Okay, so now the A2 minus being replaced by the equivalent. Okay, so finally you end up with this deal. So this is at equilibrium now, you know, this H total at equilibrium. So this is the x you solve for. So there's only one x, right? This final expression, one x. And you prepare the experimental quantity. So this is analytical concentration. So you know this numerical concentration. So plug that in, and solve the x, and knowing the Ka value. Okay? So for exercise, you do this one. For sulfuric acid, let's employ this concentration, 0.04. Okay, so this is the C value. Okay, the Ka is this magnitude. So at home, calculate the pH and compare your answer with your study group members and your classmates. Okay, so you can argue about or cheer, whatever is the low. Okay, do that. So you can use whatever calculator, fancy calculator you have, or derive this to quadratic equation. It will be an exercise for you.